Hi there. Welcome to this lesson on Pure Mathematics 3. We're on Chapter 3, Trigonometric Functions. We're on Part 3 of 3.4. And in this lesson, we'll be looking at how you solve trigonometric equations, more complex ones than we've looked at in previous lessons. So the first example we have, we're asked to solve 4 cos squared theta plus 3 sine theta equals 4. And we're asked to find all of the solutions in the range 0 to 360 degrees. If you have a trig equation to solve, one of the first things that you really want is everything to be cos, everything to be sine, everything to be tan. You really want everything to be the same trig function. So the first step on this question is making everything into sine thetas. Now I'll let you have a go yourself first. Pause the video and then come back to me when you're ready. Okay, well, have a look at this. So as I said, we really want to have all exactly the same trig function. It's nearly always the best way to solve any trig equation of this type. Well, the cos squared we can change. Cos squared is equal to 1 minus sine squared theta using the identity. So instead of writing this, we can write 4 into 1 minus sine squared plus 3 sine theta equals 4. Multiplying out the brackets, we'll get that. Collecting all the terms together, we'll get 4 sine squared theta minus 3 sine theta equals 0. And I collected them all on the right-hand side in order to get rid of the minus in front of the sine squared. It's easy to trip up on this, but this is one of the easiest things to factorize because you've got sine theta common to both terms. So you just take sine theta out of the brackets, and that leaves you 4 sine theta minus 3 inside the brackets. When we multiply these together, we get 0 for the answer. The consequence of that is one of the things must equal 0. So either sine theta equals 0 or 4 sine theta minus 3 must equal 0. Which means sine theta equals 0, or just quickly solving this, that means sine theta would equal 3/4. Two possibilities. We'll have to consider them separately from each other. So we'll look at sine theta equals 0 first of all. I think the best way to solve this is just to draw a very quick sketch of sine theta. And that's what sine theta looks like. Now we want to know when sine theta equals 0 in the range 0 to 360. So we're only looking at the right-hand half here between 0 and 360 degrees. And we want to know when the curve equals 0. Well, it equals 0 when it cuts the x-axis. It does so here, it does so here, and it does so here again at the very end. So at those 3 points, sine theta is equal to 0, and we can just read the answers straight off there. So that means in the range we've been given, theta could be 0, it could be 180 degrees, or it could be 360 degrees. That was the first possible solution. The second possible solution was that sine theta equals 3/4. Now to find the first solution, we use a calculator. So you just do inverse sine of 3/4 and see what you get for the answer. Well, you get theta equals 48.6 degrees. What I'll do is I'll sketch that on here at 48.6 degrees, and 3/4 means on the y-axis, it should be at 3/4 or 0.75. So it'll be around there, about 0.75 on the y-axis, 48.6 degrees on the x-axis. We're looking for all the solutions between 0 and 360. So we're looking for any solutions at a height of 0.75 in this range 0 to 360. Well, there's only one more. There'll be one here as you come down again after the maximum. The easiest way to find that is using the symmetry of the curve. This distance here is from 0 to 48.6 is 48.6, which means the distance coming back from 180 must also be 48.6 for the matching point coming down. So this point here will be at 180, take away 48.6, and that gives us 131.4 degrees. So all we're doing is using the symmetry of the curve around the maximum, because it's perfectly symmetrical, around that line going through 90 degrees. Now we can see the whole of the range that we want from 0 to 360, Sometimes you have to go hunting for extra solutions, but in this case, you can see that there are only 2 solutions. Any other solutions would be back here before 180 or minus 180. Any further solutions would be up beyond 360 degrees. So in the range we've been given, those are clearly the only 2 solutions. So we can now say there were 3 solutions for theta equals 0, 180 and 360, and then 2 solutions when theta was equal to, or when sine theta was equal to 3/4, which are 48.6 and 131.4. It's normal to write the answers in order from smallest to biggest. So the best way to write the answer down would be, is theta could be any of those values heading upwards. Okay, example 2. Now this second example is quite a lot more complicated. There's a few things that are more complicated about it. The 2 most obvious ones are we're working in radians instead of degrees. Now just about everybody finds radians more confusing than degrees. So don't worry if you do too. For pi, well, that'll be 720 degrees, but we'll be working in radians. But I often just do a quick conversion in my head, just so I know exactly what I'm looking at. So it'll actually be 0 to 720 if we were working in degrees. The second thing is we've got half theta here, rather than just theta. Now don't worry about that. It doesn't become an issue till late on in the question. But later on it does become an issue and you have to negotiate it in the right way. I'll let you have a go at this question first. Once you've had a go, come back to me, but you can pause the video. And as I say, when you're ready, return to me again. Okay, tricky question this one, but I'll go through the whole thing with you. So we've got cosec squared theta here. Well, there's a trig identity, 1 plus cot squared equals cosec squared, which means 1 plus cot squared of a half theta is cosec squared of a half theta, if we just change the angle from x to half theta. And we can use that to change the cosec squared a half theta here. So changing the cosec squared a half theta, we can write down that equals 1 plus cot squared a half theta, using the standard identity. The reason for doing that is because then everything in the equation is cot. Solving this type of equation, you want everything to be the same. And now everything is. We've only got cot of a half theta, nothing else. Multiplying out the brackets and collecting up the terms will give us that. 4 cot squared of a half theta minus cot of a half theta minus 5 equals 0. Now this is just a normal quadratic. It just looks a little bit strange because of the angles and because of the cots. But we can factorize that. It factorizes into 2 brackets. 4 cot a half theta minus 5 and cot a half theta plus 1. And we know that if we multiply these together, we'll get 0 for the answer. That means one of these brackets must be equal to 0. So either cot a half theta is equal to 5 over 4 if this first bracket equals 0, or cot a half theta is equal to minus 1 if this second bracket equals 0. A bit like on the last example, we've got 2 solutions and we need to think about them independently. This first solution, or the second solution rather, looks like the easier one. Cot a half theta equals minus 1. So I'll do the easier one first. The first thing that's helpful to do is change the cots to tans, because when we use our calculator in a minute, we can only use tan, we can't use cot. So just changing them to tans means doing 1 over. 1 over cot is tan, so 1 over 5 over 4 is 4/5. The fraction just turns upside down. And tangent of a half theta, well, 1 divided by minus 1 is just minus 1, so it doesn't change at all. And as I said, we'll look at this tan half theta equals minus 1 first of all. We don't really need to draw a sketch this time, because tan theta is a lot easier to work with than sine or cos theta. So we find the first solution rather, using our calculator. So you do inverse tan of minus 1. That'll give you the first solution. Inverse tan of minus 1 is minus pi by 4. That means half theta could equal minus pi by 4. Now the reason why tangent is easier to work with than sine and cos is to find extra solutions all you have to do with tan theta is add or subtract multiples of 180 degrees in order to find any other possible solutions. A bit more confusing if we're using radians. You need to know that 180 degrees is pi radians. So if we're working in radians, we need to add or subtract multiples of pi radians. So the next solution will be minus pi by 4 plus pi, which gives us 3 pi by 4. Next solution, add on another pi. That'll give us 7 pi by 4, and 11 pi by 4, and so on and so on and so on and so on. You never quite know where you need to stop with these things. You need to keep half an eye on the range here. We only want solutions between 0 and 4 pi. And also you need to keep half an eye on this. We've only found half theta so far. Well, if those are the values for half theta, the values for theta, which is what we actually want, will be double all of these. So if we double minus pi by 4, we get minus pi by 2. Doubling the others gives us 3 pi by 2, 7 pi by 2, and 11 pi by 2. At this point, I think I would be looking carefully at the range. We only want values of theta greater than 0, so we're not going to need this first one, minus pi by 2. 11 pi by 2 is 5.5 pi. Well, that's bigger than 4 pi, so this last one is also outside the range. It is always a good idea to find the first value which you don't need, because then you know that you have found all the values that you do need. But anyway, those two values we can discard. All we need are those two in the middle, 3 pi by 2, 7 pi by 2. They're the only two solutions in the range that we want. So that's for tan 1/2 theta equals minus 1. Now, if you remember, there was a second solution which was a little bit more complicated. The second solution we had was that tan 1/2 theta could equal 4/5. Now, 4/5, when we start doing solutions of this, we won't get multiples of pi this time. We'll just get decimals. That's all the calculator will give you. So for that reason, I have just changed 4 pi into a decimal. 4 pi will be 12.57. That's the number we'll be needing to keep an eye on later on. The method is still the same though. We use our calculator to find the first solution. So we do inverse tangent of 4/5, inverse tangent of 0.8, and that gives us 0.67 radians. So that's the first solution. We add on multiples of pi to find all the other solutions. Now I could also subtract pi, but if I subtract pi, I'll have a negative number. And I know from here I don't want any negative numbers. So I'm not going to bother with subtracting values. I'm just going to do the adding values. If I add pi to that, I get 3.82. Add pi again, I'll get 6.96. And so on and so on. I've stopped there because I know this is half theta, which means that theta is going to be double these values. So finding theta and doubling all of these, I'll get 1.35, 7.63, and this third one, when I double it, becomes 13.92, just outside of the range that I need, bigger than 12.57. That means I know I've gone far enough. I'm not going to need this 13.92, and I don't need to go to any of the earlier ones because they'll all be negative, and I don't want any negative solutions. Theta has to be greater than 0. So this solution will get discarded, and all I will need is the other two. Theta could be 1.35 or 7.63 radians. The question's basically finished now. It's just a little bit of tidying up to do. So the first set of solutions we got were for tan 1/2 theta was minus 1. We had those in terms of pi. Because our other solutions are decimals, it makes sense really at this point to change these two into decimals as well. So 3 pi by 2 and 7 pi by 2 as decimals, they're 4.71 and 11.00. The other two solutions that we found were 1.35 and 7.63. And it's a good idea when you write down the answer just to put all of these 4 possible solutions in order. So that would be the best way to write the answer. Theta could be 1.35, 0.71, 7.63, or 11.00, and all of those are in radians. Okay, if you've got the textbook, turn to Pure Math, turn to page 60 rather, turn to exercise 3D. Question 3 and questions 8 to 12 deal with this type of question. Thank you very much for listening, and that is the end of the lesson. So cheerio.